record, and then I open a screen, and from there I can show you what I'm doing exactly, so you guys can follow what I'm doing. So I have here my course documents. I prepared some slides for you. So 3300 lectures, right? I don't go in order, so
Professor, how long do you want the PowerPoints for the presentations?
You have as a group 10 minutes, right, for presentation and everything. Show me the report. We go together on it. I can ask questions for individual members to see whether that you guys are, literally work together or not. That's basically what I'm also looking for.
Okay, thank you.
You're welcome. Anyway, let me put some stuff there in front of you, because I would like to show you some information. And also, one of the things I wanted to mention, we can actually push the power below 0.104. Because, what is the maximum frequency we have at the moment? 100 megahertz, right? If you want to go in a low power, you have to decrease your maximum frequency. I don't know what's going on with this, but it takes forever. Did I tell you about this funding stuff? Did I mention anything about funding for you last time, for those people who would like to apply for scholarship?
You have not mentioned.
I didn't mention, right? So 1 second. Laura Elkins. Give me 1 second. I will find it for you. One. It was last week, and I wanted to send it to you guys, but it seemed that I didn't send it to all of you. Just 1 second. Anyway, we're gonna make here content week 5, and then sign yes, and from there we go here, and I say here timing slides. No, 1 second. Before go here, and then I say supporting material, and from there I will go ahead and say timing lecture, and that was and 3300 lectures. Let me see which one was lectures 688. Okay, 61. Okay, sounds good. Now I want to find the email, right? 1 second. Excuse me. Was funding last week, so funding. You know what? I think I sent it here, so let's see. Okay, here. So I'm gonna put something on the chat for you guys, okay? Everybody look at it, please. Let's see, admin here. Chat. You guys can see the link, right? You see the info. I shared something with you in the chat. Here, this link. Everybody can see the screen?
Yes.
Yes, the deadline is September 25th. So please, if you think you can do it and you can even get some fun, that would be really good, right? You can do it on the work on the circuit we are doing or something else. It's up to you. Okay? All right. It's broken? How? I already clicked on it and it's working. Yeah, it's the same link.
Yeah, it appears that the link in chat does take you to a file not found page.
Let me open it. So I can take this one. Here. Can you click on it now? I click on it now and see. Yeah, it's working.
Yes, that one works.
Yeah. Okay. Okay, let me open my other tab and I start the lecture. And from there, we can move into the Vivado. So Vivado, Zoom.
So, Professor, tomorrow's going to be.
Khaled? Hello? Hello? Where did he go? I don't know.
Khaled asks in the chat.
My mic is acting weird. I was saying tomorrow's going to be both. Wednesday is going to be both labs.
Yes, please.
Professor, can you hear me?
Yeah, I heard you. Yes, I said yes. Yes, it is. Okay?
Okay.
Let me get it in the CTSP file. And then, from here, look at right. Peter is waiting. So is Peter. So push Peter. And then, we're looking for the 3300.
But is 10 minutes going to be enough for both labs?
If so, I will extend it. We have a lot of time, right? It's from 11:30 to 2:15, right?
Yeah.
So we'll have time, so don't worry about that.
Okay.
Okay, everybody can see my screen, or I don't think so. No, you see my screen, yes. Okay, you can see my screen, right? And you have a copy of this, right? Now I showed you under the supporting material. Here. Okay, so you can go under the course document, week number 5. And then, I made a subfolder there is called supporting material. You click on it and you will find the same identical material. So you guys, if you would like to write on the top of it. That makes sense? Huh? Hello?
Yep.
Okay. Now, what I want to talk to you about, it's very important thing in circuit. So circuit, if you understand timing in circuit, that means you understand circuit. If you understand how to deal with power, that means you understand circuit. That makes sense? So circuit, the most important part of it is the timing, how to allocate resources, and optimization. Optimization is a very important thing in the circuit. So if I go in a timing, I need to learn something. When I say timing, does it relate to the combinational circuit or sequential circuit? From your point of view, when I say timing, is it sequential or combinational?
Sequential.
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 Yes, but you know, also in the top of that, combination still have a timing, right? That makes sense?
Yeah, it has the critical time and all that, right?
Exactly. Every single piece in the every single piece in the sequential in the combinational circuit, it has a response time. And you know, the path, the longest path between the input to the output, this is what we are carrying in the combinational circuit. We call this what? Critical path. You guys agree? And we already have an example about this one bit for other in last week or so, right? So
Yes.
we care about the worst case path, or we call it critical path between input and output. Also, we have to think like we are working in a real application. Yes, we learn in the 2300 AND gate, we learn OR gate, we learn about what NOT gate, and we heard about those three guys are what are the basic important gates, right? Then you know we start adding pieces together to have a NAND gate, NAND, and NOR, and then you know we got the XOR and XNOR. Do you guys agree? But we figure out that you know while we are working in the 3300, as I told you, everything built based on the NAND technology or the NOR technology. Do you guys agree?
Yeah.
So everything in the to be NAND or the NOR based design. Right? Now we are working on what's Verilog, and we are targeting this Verilog to hit what FPGA, right? So now Verilog as an example of the HDL, which is stand for hardware description language, we are deploying on FPGA. What does it mean we are deploying in FPGA? That means you know the resources we are using as our FPGA resources. What typical resources on FPGA we have? We have LUT, FF, BRAM, and DSP. Did you see those? LUT, which stands for lookup table, and you know there is a set of slides I will share with you later about how the FPGA internally work. Then you know there is another one here called FF, which stands for what? Flip-flop. So that means you know while we are saying flip-flop, that means you should go back to the 2300 and you will look to what different type of flip-flop. How many flip-flop do we have?
4 types.
4. Can somebody remind me what is those names are?
T flip-flop, JK, P flip-flop,
T, SR.
SR,
and FR, yeah.
FF, T, and SR. And what is the fourth?
JK.
JK.
JK. What exactly we need to learn out of those 4? The truth table, characteristic table, which is state table basically, and the excitation table. Do you agree? So we just need the truth table and the characteristic table, which other people call in the books state table. And the last one is called excitation table. If you know those 3 guys, you will be done. Make sense? Now, and if you know how to use NAND gate and you equivalent everything by NAND gate, then you are set. But in Verilog, actually, the same code you wrote, if you go into ASIC, guess what? Everything will be translated to be NAND gate. not lookup tables. So pretty much you can imagine this lookup table as what? Bunch of gates. It's a combination, it's elements representing the combinational behavior on the FPGA. While the FF is the one is for the flip-flop, that means sequential circuit. And this one is acting as a memory, and this one is working for the specific floating point operations like adding, subtracting, multiplying real numbers. Okay, so we know this maps thing. I wrote it everywhere in front of you, and hopefully you understand what I'm saying. But we need to talk more about sequential circuit. So the sequential circuit has two important timing. If I know those two important timing, that means I can safely get my design working properly with the current maximum clock frequency without going into something that's called negative slack. Okay, so we have something is called setup time, while we have something else is called hold time. So we have setup time, hold time. So in terms of studying for this course, you know what you need to know. You need to remember the definitions. If you understand the definition, you will remember the definition. You can even write it by your own words, right? So the setup time is a timing parameter associated with sequential device. So we agree that, you know, it is something based on the sequential circuit. Everybody agree? And when I say sequential device, that means I'm referring to flip-flops. What else actually can be working as a sequential device? It's the latch, right? And the latch is basically is not stable enough. That's why people use multiple latches to build what? Flip-flops, right? Exactly. So the setup time is used to meet the minimum pulse width requirement for the first master latch make up the flip-flop work. What does this story mean? So, you know, there was latch working if you open the flip-flop, if you open the box of the flip-flop. That's why I asked you to do with the lab number 1, everything in the structure modeling. So you're gonna see latches inside. So basically, there is a positive edge of the clock and there is negative edge of the clock. Everybody agree? So I have a clock here, right? Here is my clock. If I go from the low to the high like this, that's called what? Positive edge of the clock. If I go from the high to the low like this, they're going to be the negative edge of the clock. Everybody agree with me? So this one is a positive, this one is the negative edge of the clock. So if I go from the low to the high, there is a designated latch will take care of the process of the chunk of data inside the flip-flop. So when I say the master, that means I'm talking about this one. Okay, I'm talking about the moment that I'm going from the low to the high. Make sense? More simply, the setup time is the amount of time that an input signal, that means a certain input signal going like D flip-flop. What is the input signal for the D flip-flop is D, right? Then input signals must be stable before the clock ticks in order to guarantee minimum pulse width and thus avoid metastability. What is exactly I'm saying? Now I have my clock. Now I have a clock. Can you see the clock here? Look, in front of you in the circuit here. The clock is going from the low to the high, right? The input, which is the D flip-flop, it has to be stable in this period of time. Then the transition to the output will happen. Again, if I want to see my output equal 1, I should have the 1 on the D at least like this. So if it go before this line, then I will see after the positive edge happen that, you know, the output is equal what? 1. But if my input is going like this, then still also I will see the output after the tick of the clock. When I say tick, that means, you know, positive edge happen. Then the output, it automatically will be what? On. But if I find my input is like this, did you see that? Here's the input, right? But this period of time before the positive edge happened, look this part, right? Is a smaller than the designated area here for the setup time. Do you agree? Then what will happen? We're gonna go in something is called metastability. That means the circuit is unstable. That means I might can see 1 as an output, I might can see 0 as an output, I might can see X or Z as an output. Is it clear so far?
What was its name again?
The thing that I'm talking about?
Yeah, you said it a second ago.
Setup time. Oh, the other the one.
No, the instability.
It's written here. Look here. Before the clock ticks, in order to guarantee minimum pulse widths, thus avoid possible metastability.
Yes.
It's in the definition. Again, so my clock is the train of pulses. Everybody agree? And I'm looking for events in the clock. Can you go over why the last case puts into the metastability? Of course, I can do that. So again, now I have my clock like this. Here is my clock. The anatomy of the clock like this. I have a clock. It's going from the low to the high. Let me get a different color like this. So I'm actually looking into the events in this area, right? Event. And this event is called positive edge. Do you agree? Positive edge. Right? Okay. I'm going into the, let me just make a different color. Here is my flip-flop, right? I have here the clock. And basically how it look like this, that means, you know, every positive edge, the input will be the output, right? Everybody agree with me, Ashley? So you already have here D, and here you already have Q as an output, right? Yes. Okay. So now, if I'm assuming that my input, if I assume my input is equal 1, so that means after the positive edge, the Q will equal 1. Do you agree? Because, you know, I know that, you know, on event, Q is equal D, no matter what is the value, right? Okay, so now my assumption, D is keeping flickering. It's like going up and down, right? But if I want C, Q is equal 1, I have to be sure, I'm gonna make a different color here. There is a zone here. This zone in front of you, we call it setup time. Within that zone, I have to be sure my signal is what? High. Otherwise, the circuit will not give me the output I want as a 1. So in that case, I'm looking, okay, I'm a person who would like now to decide my D to be equal 1, right? So let's have multiple assumptions here. If I assume my input when high like this, okay, my input is high. This is D, right? My input is high before the period of the setup time, right? I'm expecting the output to be what? 1. Because, you know, if my D is equal now, let me have a different color like this, is here. It came like this on the edge, right? Here. Still the output would be equal 1. Why? Because, you know, the 1 went high enough into the period of time, which is the setup time. Now, give another assumption, which is the D was high here, but is low like this, right? If you notice, this period of time is smaller than this period of time. Do you agree, Ashley? So since this period of time is smaller than this setup time, I don't guarantee that the output will be equal 1. The output will be crazy. And that's called metastability. That means the output, I don't know, maybe it can be 1, maybe one time it will be 1. When I simulate it again, it will be 0. Maybe it will be X, maybe it will be Z. So while you are designing, you have to be sure, the metastability will not happen. Can you see it in simulation? Yes.
Professor, so basically, as long as the setup time, or as long as the high goes within or before that setup time, it should be fine. But if it's shorted, if it's shorter than that setup time, then it might go into metastability.
Metastability or charisness, or basically hazard. Something wrong.
Okay.
So, okay. Can you see it in the simulation? You will not be able to see it in the simulation. Why? Because simulation is working in what? 1 or 1 is equal 1. Simulation is not adding timing aspects here, right? Simulation is saying, okay, every positive edge I will go high, that's it. But who will notice this? The logic analyzer. So after you finish working, you will go in something on Vivado is called timing report. You're gonna go in something that's called timing report. Do you agree? In the timing report, it will come and tell you what is, did you meet the setup time or the hold time or whatever. And from there, you can understand whether that you need to make modification in your circuit based on this to decrease or increase based on the requirement. So far, so good?
Yeah.
Okay. I just want to be sure that everybody understand me. It is very important. Okay. Now, okay. Let's go to the whole time. Okay. So we finished the setup. Now we're gonna go to the whole, right? Whole time. It still is associated to the flip-flops as a sequential circuit, right? And the whole time is used to further satisfy the minimum pulse width requirement for the first master latch, which is fine, that makes up the flip-flop. The input must not change until enough time has passed after the clock tick to guarantee the master latch is fully disabled. What is this meaning? It means the following. After the event happens, still I need my time to be high, the input to be high. So that part, it will be the whole time. So the inputs going into 2 stages, right? Before the positive edge and after the positive edge. Before the positive edge, you have to be exactly the same as the setup time or a little bit bigger. After the positive edge, you have to wait a little bit of time, which is called also hold time. If you wait this and you wait this, the signal, it will completely pass to the output as you want. Okay, so here's the event. Before the event, the amount of time is called setup time. After the event, which is a positive edge, is called hold time. Is it clear? If you fulfill both of those guys, that means, you know, your output it will be equal to D. Q will equal D. So far, so good?
Yeah, very simple.
Very simple. See, it's very simple, but it's very tricky. Now, the entire subject, digital logic design, is very simple. So this is just to make sure that we get the right output. Exactly. How can you get the right output? When you will design the maximum frequency. Do you agree? So if you make a maximum frequency very, how to say, if you run really fast, that means maximum frequency is fast, right? So what does it mean maximum frequency is fast from your point of view? Somebody give me an example. That means 1 over F is equal T. And that T, it will be the duration of this clock. Then, as we know what is definition of clock is T divided by 2, T divided by 2, the period. So if your clock is getting shorter, that means your setup time, hold time is getting smaller, then it will be completely hard to what? Meet the timing.
So basically T over 2 has to be hold time minus setup time.
Huh? No, it's not like that. It's not that simple. Still, you know, I'm just, you know, just wait a little bit and I will come to this conclusion, okay? But anyway, let's go back to the point. Now, maximum frequency is equal 100 megahertz. So what is the duration of the clock from your point of view? Is basically T is equal 1 over F. In that case, it's gonna be what? 10 nanoseconds. So what does it mean? That means I have here my clock. This is 5 nanosecond, and this is 5 nanosecond, and then it's gonna repeat itself over and over, right? Because I make it 5 nanoseconds, it will be easier than, you know, if I make 100 megahertz, instead of it gonna be running in the 250 megahertz. If I run in 250 megahertz, so that means the T is equal 4 nanoseconds. 4 nanoseconds, if I look at it, it's gonna be like this. 2 nanosecond here, 2 nanosecond here. So that means the hold and the setup time here, it will be very what?
Small.
Very small. So that means you are doing what? You are tightening your constraints. That means it's very hard for you to meet the requirement. You have to be very clever enough to meet the time. So you understand what I'm saying now? If you reverse engineer what I'm saying, that means, oh, those guys will affect on my design. So that means it's not just I connect 100 megahertz to the board and it will work. Because maybe the way I wrote my hardware description, language description of a problem, it wasn't tight enough on the critical path, so then I will have a problem.
So to be safe, would you say that we can make T instead of T over 2 equal hold time minus setup time? Would that be like a safe bet?
I will come to the equation. It's not simple at this, but example for this, while you are building sequential circuit, you are not just building sequential circuit. You are putting combinational circuit as well in the middle of the sequential circuit. This is the real life, right?
Yeah.
So then, you have to calculate critical passes and you put it in, and I will show you the equation. But I just wanted to show you, even it looked really simple, but it's very helpful while you're writing your code. So that's why we are no longer just writing code. We have to draw circuit on the top of on a piece of paper before we will go write our code. That makes sense? Anyway, we learned the setup time, we learned hold time. What is exactly I need from you? So to be clear for you, you have to understand what is setup time, what is hold time. You can write it by your own word. I'm still fine with that as a definition. And it can be very good question for you in the midterms or the quizzes or the finals. And let me tell you something, most important thing for me, your interviews. Since most of you guys, when you will graduate, you will apply for the fresh graduate engineer, right? So these type of questions are very famous. I have a friend of mine, he applied for principal investigator position. Have you guys heard about such a kind of position? There is a position in academic and industry, it's called principal investigator. And guess what? What was the questions? It's called principal investigator. Principal investigator. That's a title of a job for Fpga. Guess what was the first question for him? They asked him, what is the difference between setup time and hold time? Can you imagine? So they asked this question for even like a young engineer and experienced engineer as well. Anyway, now as a normal thinking, we need to talk about the maximum frequency. So we came into the point of maximum frequency after we understand something before and after. So what is maximum frequency? Maximum frequency is the maximum frequency oscillator can generate for making the circuit work safely without going into what? Metastability. Or the circuit will be crazy. Make sense? Again, so when I say maximum frequency, when I build a circuit, if I, and I say my maximum frequency is 200 megahertz, what does it mean? It means my circuit can be running in from 0 to 200 megahertz. I can make my circuit run in the 1 megahertz, it still will be a function. I can make it in kilohertz, it's still functioning. But it cannot exceed the 200 megahertz. If it's 201, right, that circuit will be acting weird. That makes sense?
Yeah.
Okay. So that's basically the definition. While we are doing this, we are thinking about, the circuit, it will be very, very, very mature enough to be combinational with sequential. Do you agree? So that means my circuit is not just combinational. My circuit is not just sequential. My circuit is basically a combination between sequential and the combinational circuit. So that means I have to look into something is called, I'm going from propagating into the low to the high. You remember when I go to the clock, I go from low to high, high to low, right? Here, you remember? Look, low to high, the other one high to low, right? Then I define multiple terms. So, in the propagation delay, in a circuit like AND gate and NOR gate, we have something is called propagation low to high, and I have this, it can be minimum or maximum values. So that's why I have here minimum low to high, minimum high to low, maximum low to high, maximum high to low. And that's all the 4 things we have. Somebody will tell me, but Professor Ali, we don't have a clock. So why are you saying low to high, high to low? I have a question for you. Are we in a binary system or not? So that means the output will be what? Will be shipped as a low and high, right? Do you understand what I'm saying?
Yes, so a 1 is a high, a 0 is a low.
Exactly. And you know, the output will be shaping as a bunch of 1 and 0. It's not, of course, like acting as a, how to say, it will not be acting as a clock, because you know the clock, it has a specific requirement, right? Everybody agree? The clock is like this. The duration is called t, and the on period is t divided by 2, and the off period is t divided by 2. But normal inputs and outputs are like 1 and 0, no matter what is the duration, right? Anyway, for the flip-flop, we need to think about also minimum and maximum. So do you remember when we came into the figure here, and I told you the minimum 1 is here, but then I told you, oh, you can even extend outside the minimum. So also you need minimum and maximum, right? So the same thing here. So you're gonna have propagation delay for the flip-flop internally because it's a bunch of latches. And also you're gonna have TSU, which is called setup time, and then you have TH, which is called hold time. Okay? So combinational circuit is just a propagation delay, and the flip-flop, it has TSU and TH, which is the hold time, and also it has some propagation delay as a normal circuit, because you know, end of the day, if you open the flip-flop, you will find also latches, bunch of NOR gates or OR gates. And I believe in 2300, if you remember, what was the main component in latch? Somebody remind me. NOR or what? NAND, right? So I remind you, if I would like to make an NOR latch, do you remember this one? That was a NOR latch. If I wanted to make it NAND latch, it was like this. Right? So end of the day, we have what? Gates. So that means somehow we're gonna have TPL, THL, TLH, PPH. That's why flip-flop also have a propagation delay, plus that little itty bitty trick of the clock itself from the setup time and hold time. Okay? Some facts came out of the reports written by a couple of scientists from the Intel. Intel is a well-known circuit company, built processors, right? So it says that, you know, flip-flop, normally the setup time is about 10 to 3 times of the propagation delay of the NOT gate. But one of you will come and say, Professor Ali, you told us there is NOT gate, you know, everything is NAND gate. I can tell you, if you have an AND gate like this and you get the 2 input to be like that, this is NOT gate. Right? So full time is basically 1 to 2 times of the response time of the inverter with also NAND gate. That's an approximation. So if somebody asks you, which is very important questions for the industry, if you understand that, you know, the response time, and I mentioned before to you the response time of gates, and we made a calculation in the critical path before, right? So the setup time of any flip-flop, it varies between 3 to 10 times of one inverter, a response time. And the whole time is 1 to 2 times of the one inverter as a response time as well. Okay, everybody with me on the same page? Everybody agree? Everybody fully understand what I'm saying? Now, we need to go into something which will help us to understand the Vivado timing report. So there is something well known in the EDA. Have you guys heard about EDA tool? EDA. How many of you heard this expression, EDA? EDA tool. Let me find it to you and I send it to you. That's better actually. EDA tool is called Electronic Design Automation. Electronic Design Automation. It's not data analysis. Electronic Device Design Automation. What does it mean? You, before in the 2300, were going to use the breadboard, right? And you're having a bunch of wires, and those wires are connecting pieces to each other, right? And this is manually by your hands, right? If you add the automation aspect to it, then it's gonna be EDA tool. So you are doing EDM, electronic design manually, right? So what is the example of the EDA tool we have in market, right? We have Vivado for Altera, for Xilinx. We have Quartus for Intel. We have Cadence tool for ASIC. We have Synopsys for ASIC. We have Assembly. We have Mentor Graphics for a simulation. And you guys are using the simulation on FPGA. It's called what? Model Sim. All of those guys from the family of EDA tool. So now is it clear to everybody? EDA tool. So while the people are working in EDA tool, they need to have a mathematical model will help them to identify the time. They're gonna embed it inside the EDA tool, then it will be automated. So what is this called? This family is called STA. So if anybody asks you what is STA, is a static timing analysis. Static what? Static timing analysis. So what is a static timing analysis? Here is the information. A method of validating the timing performance of a design by checking all the possible cases. So you remember, whatever, practice I made in front of you, and I made the one bit full adder, and I start making, highlighted paths, and then, we said the name of these paths. So basically the EDA tools, after you finish the whole entire design you made, it will start automatically identifying the passes between the input and output. No matter what is inside this between an input and output as a sequential and the combinational circuit. Then it will go ahead and start calculating the timing of every single path. Then it will go ahead and decide the maximum frequency for you. And that's basically what Vivado does, and you don't see it. So Vivado exactly doing what I mentioned to you, but automated, using the STA, which is a static timing analysis. Sounds good? So we have two different types of circuit design. You guys remember from the 2300, if you don't remember, I can tell you. We have circuit is called synchronized circuit, and we have circuit is called asynchronized circuit. So somebody can tell me what is the difference between synchronized versus asynchronized?
One is dependent on the clock, the other isn't.
Mario, what do you say?
That was Tristan.
Tristan?
No, I was just saying synchronous is all connected together while asynchronous is independent.
So, Khalid, what you're saying?
I said one is dependent on the clock, the other isn't.
Exactly. So the one will be heavily in any implementation is synchronized. The one is specified for certain missions is asynchronized. What is the circuit is basically can go into low power, the asynchronized. But it's very hard. Like, you guys were working in the lab number 1, you made everything combinational, right? You came out into a conclusion that, your power, it was 6 something watt, right?
Right.
Yes.
Then you have to put the sequential aspect, which gonna what? Make it not 100% sequential, not 100% combinational, and it's gonna be asynchronous. That's why the maximum frequency will be, sorry, not maximum frequency, the power will go down. Anyway, so any timing you have to think about it, you have to know the classification of whatever we name it as a path, right? One of the possible paths we have is the register to register path, like a flip-flop passing data to flip-flop. That's a possible path. The EDA tool will identify it as a path for the static timing analysis. The second possible is the primary input, that means the IO. So you have an IO connected to a register. So that actually can also be a path. Then the third in the line is basically the register going to report an output. An example for this, for your circuit in lab 1, you can make a combinational circuit. Part of it will be connected between the input to the flip-flop, while the output will be connected from the output of the flip-flop connected directly to the input and output ports. They're going to be also combinational circuit. So that can be a passive. Then you have an input to the output, like, you know, input to the output, and there is a bunch of what gates. That's also a pass. So those are the possible passes we should have. We need to have an example so it will store this information in our head so we will never forget. Everybody agree? So the example we can have there. So here's a circuit in front of me. The structure of the circuit is the following. I have an input and I have an output. It's called Z. And the signals are traveling from A to Z, going in a different path, right? Also, if I look to the circuit, is this circuit a synchronized circuit or asynchronized circuit from your point of view?
Asynchronous.
This one is what?
Oh, no.
No, you're fine. What you're saying?
No, this synchronous because the clock goes inside the...
Exactly. Let me tell you why it's synchronized. Because, you know, these two flip-flops having the same clock source. So that means the two pieces sequential, the two pieces timing elements inside the circuit are reporting on the same clock. If you want me to make it for you asynchronous, that's not really hard. Look what I'm gonna do. I can just come ahead and say, this is a clock 1 and this is clock 2. So clock 1 and clock 2, they don't have any relation. Then the circuit is asynchronous. That makes sense?
So just to make sure, for the synchronous circuit, it has to, like, the one clock has to be the one that is used for the whole thing, right?
Yeah, that means the whole circuit is reporting on the same clock.
If we have just one other clock, that's it.
That can be synchronous. Maybe, you know, the source of this one, it can be the input. The output of the master, and this is the slave, right?
Yeah, but still, we will be generating from another clock, right?
Exactly. Anyway, so now in front of you guys, I have the circuit, and I would like to do the first thing that, you know, STA will do, which is a static timing analysis. So we said the first thing that, you know, what it should do, it will start identifying all possible passes of timing violation under the worst case condition. Worst case is what? The worst case pass that I taught you of the 1-bit full adder between the input and output. So let's see what is this possibilities. So the one here says, if I have the D1, I can go here from A to D1. From A to D1, that's a path, right? And that's basically what we have here. The other path is the D1 to D2. This is the second path. Maybe I can change the color so you guys will not be confused. That's another path. Then I have, and here's the color. Of course, it passes the XOR if you notice. Then the third in the line is gonna be D2 via XOR. D2 via XOR, that means what is going to be like this. That's another pass, because, you know, have you noticed? Those guys is reporting to each other by the feedback control. Can you see it, everybody? That's actually the D flip-flop, as I said. Now, D2 to D1. Do you think D2 can go to D1? Yes. Look. D2 going like this, going like that, going like this, right? And this is the one. Then D2 to Z. Where is D2 to Z? D2 to Z. I'm going into the output. That's it, D2 to the output. Then A to Z, right? Somebody will tell me, Professor, where is A to Z? I can tell you here, A to Z. And here's A to Z. So if you identify all different passes as I did in front of you, so you did the first step of the STA, static timing analysis. Is it clear, everybody?
Yes.
Super. Now we're going back into definitions. So we defined before setup time and we defined before the hold time, right? If we didn't meet the setup time requirement, do you remember when I said there is minimum, maximum, and stuff like that? If I didn't meet the setup time, if I didn't meet the hold time, I will cause something that's called what? Violation. Again, if I don't meet the setup time, that means I violated the setup time. Do you agree? If I didn't meet the whole time, I violated the whole time. Because you know, I set up a target. What was the target I set up in this in Vivado? From your point of view, I connected to the 100 megahertz, the XDC file 100 megahertz. So that means automatically I told Vivado, hey, my maximum frequency this work. But I build a circuit will not operate on 100 megahertz. Then Vivado will consider that you violated rules. That makes sense? So I have definition of setup time and I have definition of the hold time. What is the definition of the setup time? It occurs if the data change just before the clock without providing enough setup time of the flip-flop. Ashley was asking me a couple of minutes ago, and she said, repeat this part when it will be less than the small part, right? And I made it here in front of you, and I said this part. Then I came into the conclusion, what I did now is called violating the setup time or not. Do you guys agree?
Yes.
Exactly. So I violated the setup time. So STA, it will come and tell me, Muhammad, you violated my setup time. Your circuit will not be operated on this designated maximum frequency. Either you relax the maximum frequency or you will redesign your circuit and shrink the critical path. Hold time, the same thing. I didn't meet the requirement of hold time. So my hold time, it was this area, right? Where is my hold time? It was somewhere here. This part. Or, you know, here after a clock here. If I came here and I exceeded, I went above the whole time, or maybe I make it shorter than here, then, you know, I also violated the whole time. Then the circuit is still going to be acting correct. Okay. Now, we have something, the EDA tool, that wasn't exist, by the way. The EDA tool made a margin. Did you understand what I'm saying? Margin was saying that, you know, within that margin, still I will be acting correct. And they called that margin what? Slack. So if I'm in a margin of the setup time like this, my slack either it can be positive, negative, or zero. Zero, that means, you know, I'm exactly like the setup time. Zero, I'm exactly like the whole time. But if I'm by how much percentage I'm far from violating, that's called slack. So the slack is the amount of time still left before a signal will violate a setup or hold time constant. Example, let's go back to my example here. So if you noticed in the whole time, I came into the point that, you know, I have this amount. I didn't touch completely the part, but I came here before. So I would say, oh, I have 1 nanosecond and I will violate the whole time. Or I have one nanosecond, I violated the whole time. So an approximation, how should you slide yourself back into the safe zone? So you can think, how can you make a modification in a very correct way? Then Vivado will take what you mentioned. So note, paths must have a positive or 0 slack. So when I will look to my timing, if I find my timing with negative, that means the circuit will be in a metastability. That means the circuit will not be acting correctly. It will have glitches, they call. How many of you heard about term is called glitch?
Probably everyone.
So that means, you know, I will tell you what does glitch mean. It means the following. I designed that this thing to be thrown from this point to this point and hit this thing, right? Yeah, here, and I wanted to push it to there, right? But then while I'm throwing it, it came here. And somehow it jumped to there. So the moment it went from here in the ground until it came here, that amount of time, it's a glitch. Because I didn't design the movement to be pumping on the ground and then reach the target. I designed it to make it directly go to the target. So that's called glitch. That also we're gonna learn later on. It's a part of the violation. So if I open my timing report of a certain circuit, I find that everything is positive or 0. That means I still have amount of time to play with the circuit or even increase maximum frequency without violating the time. Passes that have a 0 or very small slack are the speed limiting passes. What does it mean? If I have 0, that means, oh, there is no room for me to increase the maximum frequency. Let's say that, you know, Mario designing a circuit which is basically launching rocket to the moon. And then, you know, he designed that, you know, the computation will be running in 400 megahertz. Then he found that, you know, his slack is 0.3 positive. Then Mario came and say, oh, should I increase my maximum frequency or not? People will come and tell him, Mario, you just have 0.3 left as a safe margin. I don't think you can increase to 400 or 500 megahertz. Maybe you can increase to 450. That makes sense? Then Muhammad designed the same rocket, but then the value came to be 0. What does it mean with 400 megahertz? That means Muhammad doesn't have any room for increased maximum frequency unless he will make a very, very detailed modification in the circuit. While Khalid, when he designed his circuit, he found that the slack is minus 0.01. What does it mean? Khalid, he has to find a way to itty bitty decrease the maximum frequency by little bit numbers, like instead of 100 megahertz to be 98 megahertz or to be 97 megahertz, then he will safely back into the safe margin. Is it clear, everybody? Hello?
Yes, it is very clear.
Yes.
Now we're gonna go into the calculating timing on passes. So in the example here, we learn how to do the critical passes. By the way, the book, the chapter 2 in the book, right? It has a ton of this. It has many examples, many problems, you know? You can go ahead and look at it, please. It's very important for you. I can give you homeworks, but you know, my idea, we are in a 3000 level. We are mature enough to look into resources and see which way you guys like me to do it. Do you want me to give you like an homework, or do you guys like to do it by yourselves?
As homework, would it be due, or would you like just be assigning problems?
If I make a homework, I have to make setup on time. Like, you know, you will come and give me the results or stuff like that. So
I think as long as we know where the material is and where
exactly.
to see.
If you fully understand the material, if you open the book,
Yeah, or if you like give us the problems that you think are very beneficial for experience.
Yeah, I mean, I'm not gonna give a problem which is coming in exam, because, you know, end of the day, you know, if I give you the exam, then you know what are we gonna do. If you could tell us the chapter in the book, that would be great too. Chapter 2. Everything now, chapter 2 and chapter 1. Those are the most important chapters in this course, because it's introductory course. You know what I mean? Okay. We can, you know, once we finish, if I have time, I can open the book and then we can pick some stuff and solve it together. It's not a problem. You know? Anyway, here is a circuit, right? And the circuit is very good circuit. Why? because it's a mix between combinational circuit and the sequential circuit. Do you guys agree? We have combinational circuit here in the middle of the two flip-flops, which is something also very important in the design approaches. So I am gonna give you example. Imagine the following. Imagine that I have an input here and output like this. Here's my input. Here's my output. And I found my critical path very, very long. What people actually do, they go ahead and follow something that's called discontinuity approach. What does continuity approach mean? That means, I will truncate piece of the critical path and I put here buffer. I put like a flip-flop. Then the output, I will truncate it again to be another buffer. So that means instead of finishing this into one long line, I will make it in a very short multiple segments. So I will go and approach something that's called sequential circuits. So that means a cycle, second cycle, third cycle, I will do the work. It still is the same amount of time, but you will elevate something that's called pipelining. How many of you heard about the word pipeline? It is kind of like threading, yes. So I give you example. So, imagine the following, right? I build here now flip-flop 1, and then, I push here the data into flip-flop 2. Then I push here the data into flip-flop 3, and here is my output. Imagine that I have 14 patch of data. So I have patches of data. So patch 1, patch 2, patch 3, patch 4, patch n. See, I have n paths, right? N patches, right? So look what will happen. Path 1 will be sent to the first stage. So we call this stage 1. Then stage 1 will finish, so path 1 processed will be there, right? Now, who will be processing this data? Number 2, right? But this one is doing what? Doing nothing. So in that case, I can give path 2 to this circuit while path number 1 is going into number 2. Then you will move forward up to the number 3, and after that, you will gonna have like a Coke, the Coke and Pepsi manufacturers. Have you watched a video about how they actually manufacturing the Coke? You have a line of bottles going into a machine, cleaning it, stirring the bottle. Then the bottle will be filled with the Coke. Then it will be pushed into the securing the lid, while the second bottle will be pushed into the machine, and the Coke will go there and move forward. That's called pipelining. It's used in the factories and manufacturing and industry perspective. It's the same thing will happen in the circuit. The circuit will be pipelining. So keep pushing to each other. So the total overall will be improved. The total overall of the time will be improved. We can talk about this later in more details, but I just wanted you to think about it. Anyway, back to the example. So I have here my circuit, and I have some information about the circuit. So the circuit, the clock of the Q of the flip-flop A, this is flip-flop A. The maximum minimum is 7 nanoseconds, 9 nanoseconds. When I make it like this, that means this is the minimum and this is the maximum we have. And if you remember in the slide above, I was mentioning about that, you have TPH, TPL, minimum, maximum, and all of these things. Then the clock of the B, it has 8 nanoseconds, 10 nanoseconds. This is the minimum, this is the maximum. Then my combinational circuit, look at this, my combinational circuit, this one, I have no idea what is this combinational circuit as. Somebody can tell me what can I do in the exam? Maybe I can remove this little itty-bitty figure and I put you a real circuit. Then you know what you're gonna do. You're gonna calculate the longest path, shortest path, and you will know the minimum and maximum. You guys agree? That's one of the possible things that I can bring in the exam. Make sense? So anyway, so this circuit, it can perform in a minimum 3 nanoseconds. It can perform up to 4 nanoseconds. Then the setup time of any of those guys are 2 nanoseconds, and the whole time of any of those flip-flop is 1 nanosecond. So now we have a timing information coming out of the elements inside the circuit. So we need to calculate the maximum frequency. So in that case, we have to go ahead and check every single passes based on the STA passes or the static timing analysis. Okay, so here's the delay of the first pass. What is the first pass? It's A to B. A to B, right? A to B. In that case, I'm looking for the combinational aspect of the flip-flop. What is the combinational aspect of the flip-flop? Is the Q clock TQA. Then also I have to look into the TSU to go into the out. So basically it's gonna be the TSU of B because I'm going from A to B. I'm sorry, it's, let me clean up. Look, I'm going from A to B like this. Right? Everybody see what I'm doing? Did you see the arrow? Gonna be here, you have to get the TSU before the clock. And there, you have to give me the whole entire combination of the flip-flop. So that's why I have the TQ with the TSU. So I know that the maximum, I think the maximum is gonna be 9, plus here the TSU is 2. So that means this passes will cost me 11 nanoseconds. What is the second possible pass we have? A to C. A to C. Somebody tell me where's A to C like this? Right? A to C, that means combinations of the Q. Okay. Combinational circuit. Okay. Before the clock will tick, TSU. Add all of those guys together, it's gonna be 15 nanoseconds. Right? Are we done? Still, we have multiple passes. What are the other passes we have? B to C. B to C. So what is B to C is here? B to C. What is B to C we have? It's very easy. It's gonna be the clock, the combination of this is gonna be 10, 10. And then you know the two combinational circuit, we already have it there. It's 4 maximum, 4. And the TSU still, because you're gonna go into before the text, so it's gonna be 2, so it's gonna be 16 nanoseconds. Are we done? Still we have more. What is the others? It's gonna be input to the flip-flop A, right? So we have an input to the flip-flop before the tech. So it's gonna be what? TSU. It's just 2 nanoseconds. Then we have one from the CSU to the output, right? So now they're gonna be, give me another color. So it's gonna be this one to the output. So in that case, it's gonna be the whole QSA, which is basically in that case, it's gonna be QSA. We have it here, it's gonna be 11. So they're gonna be that 11. So far, so good. We already have now all the timing. What is the maximum frequency? The maximum frequency comes from the slowest pass, the critical pass, as we did with the combinational circuit. So what is the longest pass we have so far, guys? Is gonna be the, it's gonna be this one, 16 nanoseconds. So in that case, I will go ahead, 1 over 16 nanosecond will be my maximum frequency. And that's basically what I wrote it here. So that's gonna be the longest pass. So 1 over 16 nanosecond. So this circuit in front of you with this spec, it will be running up to 62.5 megahertz. Anybody have any questions so far?
So you said that this would make a good exam question, or just it's a good question overall?
The exam question, Mario, it will be the following. I'm just giving maybe, right? I can make it multiple stages. That's one example, right? The other possible exam questions, and instead of giving you something like circle like this, I call it combinational circuit, I can give you a combinational circuit. Like I can tell you, design 2-bit multipliers as a combinational circuit. With respect of the design we'll be using, for instance, NOR gate. And the response time, I will tell you about the whole time. With the response of the NAND gate, 1 nanosecond. Then you're gonna do the same thing I did, do you remember, with 1-bit full adder? You will find the critical path, and from there, you're going to know the longest and the shortest passes, and you can put it there.
I see.
That makes sense?
So a mix of a few different.
Combination,
yeah.
right?
Yeah.
Yes. So, Rohit, you said you are a little bit confused with the whole time, right? So the whole time, I can return it back to the whole time very quick, right? I can add extra page, and maybe that will be more helpful. Here. So look at this, right? Here is my clock, right? Can you see my clock? This is positive, this is negative. This is positive, this is negative, right? Normally, hardware designer, they design this circuit based on the positive edge or the negative edge. Everybody agree? There is no way for you to use both of them. Yes, I did that before, and I have a US patent for it, but it's very difficult. Your timing will be like mosquito soup. Okay? So for now, I'm gonna build the whole entire design to be reporting on the positive edge of the clock. So far, so good, right? So that means, what is the most important event for me? This one. The rest of the clock, useless. Okay? Now, I will make something is called what? It's called STA, right? So basically, I have something here before the tick and here after the tick. So the event is called tick for me, okay? Now, that period of time is the setup time. That period of time, that's called what? Hold time. We are talking about who the input will be going. So basically, I need my input to be up like this. If my input is high enough here and high before by this amount of time, that means that output will be 1 for sure. Now it makes sense? We only need the right time for the setup to get the right output, right? It's for both, because if you read very well the definitions, it will say that I have inside the flip-flop two latches, right? The latch in the beginning is called master latch. That master latch is responsible on what? This area. The second latch is responsible on this area. Make sense? The need of the setup and whole time, I'm coming to it. Okay, but at least you have to have, here is the edge. Before the edge, you need a safe margin for the input to be 0 or 1, and after the edge also you have to have some time, which is the whole time. Here is setup, here is hold. Okay, look.
And these setup and hold times, they remind me a lot of debouncers, no? In the sense how it's just
actually
waiting.
The whole trick of the debouncer play with the setup time and hold time.
Yeah.
It is trick of the tricks. If you learn those, you can make a lot of tricks. I'm gonna teach you guys the crazy tricks. Okay. So far so good. So is it clear now? Okay. So I can stop a little bit and ask if anybody has any question. Please, slow me down. I will just go back and repeat. Khaled, is it clear?
Yes.
Eduardo, clear?
Yep.
Tristan, clear?
Yeah, so just to clarify the comb logic, you can have anything else. Like you can build a circuit out of that, right?
Yeah, imagine that I will give you an example. I will come here and say this is 1-bit full adder designed using 2-input NAND gate with response time 1 nanosecond.
Okay.
What you gonna do?
So if we were trying to get
Then you're gonna
let's say,
then you can make like this. You come and say that, you know, C A B C N sum C out 1 2 3 4 5 6 7 8, and then 0 1 0 1 0 1 0 1 0 0 1 1 0 0 1 1 1 2 3 4 1 2 3 4, right? Then you come and make the table, and from there you come into the equation saying that sum is equal A XOR B XOR C, and then, you know, carry out is basically A ANDed with B, ORed with A ANDed with C, and the ORed with B C N, right? Then, oops, all of those guys are AND and OR and XOR. Then you're gonna build all of those guys using NAND gates, and you will make the timing, and you will make the circuit, and then you will find the longest path, shortest path, and you will define the maximum.
Okay, yeah, that makes sense. Okay, got it. Thank you.
Mario, clear?
Yes.
The rest of the course, everybody, if it's clear, write clear, or write yes or something. Yes. I love CLR. Yes, I use it all the time in my code. Okay. Anyway, thank you, Stephen. Thank you, Eduardo. Thank you, Andrew. Thank you, Chad. Thank you, Ashley. Thank you, the rest of the people. Okay. Now we're gonna go into another timing problem. So we know now the maximum frequency. We need to see how the maximum frequency will be affected using the timing. Okay. Okay. What is the story? The story is a sim circuit, right? But instead of the combinational circuit, I put you an XOR, right? XOR is representing what? Combinational circuit, right? Then I also have some timing here. The flip-flop 5 to 8 nanoseconds, the other one 7 to 9 nanoseconds. XOR is gonna be 4 to 6 nanoseconds, and gate is gonna be 1 nanosecond to 3 nanoseconds, and the setup time is gonna be 5 nanoseconds, 2 nanoseconds. If you open the data sheet of all of your gates, do you remember when you bought the ICs and you find those ICs are TTL technology? If you open the data sheet, you will find all these numbers. Would you imagine? So you can do by your hand. You can even, you know, go in your 2300, the breadboard you made, and you calculate the time. And you will be able to figure out the maximum frequency. You're gonna put it from the generator, the function generator. It's a simple. Anyway, what exactly I'm looking for in this circuit? It's a very important information to learn. What is this important information? We need to calculate the maximum frequency. Khaled was saying about, you know, the clock, you're gonna accumulating all the timing there, and then everything will be working fine, right? So if I look into it, so I will find the following, that, you know, the TB maximum flip-flop plus the TXOR maximum plus the TSU of the last one, that will be the enough for pushing data into the output, I'm sorry. So in that case, you know, one of the maximum flip-flop there is gonna be 9, I'm sorry, yes. Plus the TXOR is 6 here, gonna be added. And the TSU of this gentleman, it was what? It was 5, so 5. In that total, that means, you know, my maximum frequency is 50 megahertz. What does it mean? This circuit with this specification can be operated safely without being violating any rules on a maximum 50 megahertz. So far, so good. Also, there is some estimation for what is the longest. Do you remember when we said, you know, here is the duration of the setup time, here's the duration of the whole time. Then, you know, I remember when I told you, oh, maybe I came before the setup time, but still doing great, right? Remember that? You know, when Ashley was asking. So basically, you already have here like this, right? Here is your margin, right? If my input came like this, so that's earliest can come to, right? So in that case, I'm calculating the earliest time after rising the edge. So that means I'm after rising the edge, that means the timing after this here can safely change. How can you do this? It's basically based on the TH. The whole time you're subtracting from the minimum of the combinational circuit, and from there you can get the 1 nanoseconds. And also for the what is the latest time before the rising time, that means here. So gonna be the T N gate here, this N gate, plus the TSU is gonna be 8 nanoseconds. So you understand what I'm doing now? I'm trying to find before and after. That's also another example. I think I have another patch of slides. Let me find it so I can also share it with you with more intensive examples. So let me see. Yeah, I have another one, but I have a question for you guys. Do you prefer me to give you some time to digest what is written in front of you now, or I will continue and give you more info about the timing? Which way you guys prefer? Because this is very important. So I can give you some time. I have some other stuff I can share with you about timing, like a Slack and all of these things. But I can synchronize and glitches. So what I can do, I can move that part to the next Monday. But at least for now, what we learned so far in that part of the theoretical part of Verilog, what we learned there is something is called setup time. We learned something is called hold time. Everybody agree? We learned that what is the maximum frequency is, how the setup time and hold time affect in the maximum frequency, right? We learned that there is something is called STA. What does STA mean? You have to define the critical passes. You have to calculate the timing for every single pass. You take the longest pass and you will consider it the worst one. You flipped it, then it's gonna be the maximum frequency. We have a couple of examples about how to identify passes and how can you calculate the maximum frequency. So far, so good?
Yes.
Okay. Maybe I can move a little bit to some practical Vivado things so you guys can take some rest from the timing. Huh? So Daniel, I already posted slides, right? Daniel? It's already in the Blackboard, right? Or do you want me to post this one as well? Hello?
These slides are on Blackboard. That's I found them.
Ah, you want this one, right? So maybe what I can do, I can make a copy and send it to you guys. It's not a problem. So do you want me to put it under like a folder called notes or something? Okay, that's fine. Okay. Let's see, how can I do it? Email myself. Maybe. Then I will do it now so you guys at least can see it in a moment. 1 second. I go now inside the supplements, and there I can say folder again. It's called notes with slides. But there, and from my email, I can send it to you now, and then you can take a copy of the concept. Excuse me. Just around. Now, so I will name it timing notes and slides. And I'm gonna put it in my course. Lectures. Okay, now I go in the slides node and say create file notes Today is what? 09/21/2020. Timing will slides. Okay, so Daniel, you can find it there already. Okay. Daniel, it's on the Blackboard now. Okay, so now what we can do, we can go back into my other screen, and I can switch and turn off my my tablet, and we go into Vivado. Vivado. Let me open Vivado. Vivado 2018. Yes, screen, yes. And I'm still waiting for my Vivado to open. So a second until. One second. Vivado. Look, where's the clock divider? You know what? I'll just say open project, new project. Okay. Everybody can now see my screen. Right? Can you see Vivado?
Yes.
Everybody can see Vivado? So my question here, so you guys understand what does timing mean, right? You understand when I say timing, that means, you know, the clock is taking piece of time, and then, you know, I can count and I can tailor a new clock divider, right? One of the things that I showed you, it was the IP, right?
Professor?
Yes.
Danush's Wi-Fi cut off. Is trying to join the meeting.
Somebody?
Yeah, somebody's trying to join the meeting.
Where I cannot see. There is nothing here in front of me. Let me see what is this, so I can see stop share and see. Danush actually went out. So back. Okay, now share again the screen. So you understand what I'm talking about now. I'm talking about, you know, clock dividers. We already talked about how to use the PLL, right? Everybody remember that? Huh? Do you guys remember the, yes, one of you just remember. -1. All of you have the board, right?
Yes.
Yes.
Very good. We made the counter last time, exactly. But then, you know, we found out that, you know, the LED is not flickering enough, right? That's why we need to make a significant change in our design to make the counter getting more and more, how to say,
On a slower
slow. Yes.
clock.
Exactly. before you know, when we slow the counter, do you remember how did we do it, right? So we, I don't know why the sharing is not sharing with you the Vivado.
Well, one way could be changing the time constraints on the Vivado file on the very.
No. XDC don't play with, because it's like basically, you know, FPGA will allow you, but you know, the PCB design have been made by Digilent is basically make it fixed. You understand what I'm saying? It's gonna be a completely fixed for you, so you cannot do that much.
You can make a clock upon the clock.
No, what you can do something called clock divider. So what I can do in front of you, I can show you what I mean by clock divider. It's better to draw it in front of you, and then I come back into the writing code. One second. Okay, so here's the thing, right? Now I have a clock, right? So my clock, it's basically the 100 megahertz. Everybody agree? So what does it mean? You know, basically I have my 100 megahertz like this. And when I say 100 megahertz, that means this is what? 10 nanosecond. Everybody agrees with me?
Yes.
Yes. So now if I want to make, for instance, if I want to make a new, if I want to make a new clock out of this 100 megahertz, which is gonna be 50 megahertz, what should I do?
You could say.
Two ways. What?
Oh, I was gonna say that you could have it so that, you know, every five clock cycles, another clock increases by one.
It's not 5. No, it's not 5.
Or you.
First of all, there is 2 ways to do a clock divider. One of the way to do a clock divider is to actually use the counter bit to be a clock divider. Example. When you are building a counter, right? When you are building a counter, this counter is the following, right? Let's say that, you know, I have the counter is 3-bit. Everybody agree with me? So my counter is 3-bit. So basically it's the B1, B2, B1, and B0, right? So look what will happen. So you already have an 8 statement, right? 1, 2, 3, 4, 5, 6, 7, 8, right? When I go into the fun 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Have you noticed something? If you would like to draw this, how gonna look like? So B0 will be like this: 0, 1. Sorry, let's make it. Let's put it with the clock. So I have a clock here, right? I'm looking for those, right? Everybody agrees with me? Now I'm looking for B0. I would like to draw B0. How B0 will be? B0 will be like this. From here to here, I'm 0. Right? The second, it's from here to here, it's gonna be 1. The third, from here to here, it's gonna be 0. And you will move forward. Do you guys agree? Why? Because the circuit report every single edge of the clock. So the edge of the clock here, it makes it 0. The edge to here, it's gonna make it 1. Have you noticed something? The duration of this, it was what, let's say 10 nanosecond, 5 nanosecond. Now the duration of this guy became what? 1, 1, 2. Each one is 5 nanoseconds. So that means this is what? 10 nanoseconds, 10 nanoseconds, 10 nanoseconds, 10 nanoseconds. If I consider this clock, look what happened. This is 20 nanoseconds. Did you see what I did? Make sense?
Yep.
So from there, if I have a counter, and this counter, how many bits? N bits. Let's make it 4 bits, right? So you already 4 bits. 1, 2, 3, 4. Here 1, 2. Right? So that's gonna be 2 power 0. So that means maximum frequency divided by 2 power 0. No. You're gonna make it 2 divided by 2. So it's gonna be maximum divided by 2. Here, it's gonna be maximum divided by 4. There, it's gonna be maximum divided by 8. Here, it's gonna be maximum divided by 16, and so on. So that's a way of dividing the clock. That makes sense? So we learned PLL. Now we learn to make a counter, and then we take every single output of this counter as a what? As a clock by itself. Right? Let's see whether that what I'm saying makes sense or not on the waveform. And from there we'll come into something that's called customized clock divider. So this one is more well designed in a way that you have to go into 2 power something. But if the value of the new clock you want it to be designated in a certain thing, then Mario, the trick you are saying about, we're gonna run a counter calculating how many piece of time on it will be, how many piece of time off will be, and then you will issue 1 and 0, then you're gonna make a new clock. That makes sense, Mario?
Yeah, it's similar to what I was trying to, yeah.
Exactly. So there's 2 ways, right? One is systematic, which is basically the PLL. The other systematic is basically 2 power divided by something that's gonna be counted. The last one is gonna be you count per cycles of your old cycle, how much time it takes, then you're gonna make it on, and then reverse is gonna be make it off. That's basically the clock divider. See, so I'm just trying to make it very simple in a way that show you how the description language is not important. The more important is the way of thinking for the digital logic. That makes sense? So now I'm gonna go into the Vivado again. I need to find a way to share like the 2 screens at the same time, like the screen of the computer and the screen of the tablet. So it's not allowing me, but anyway, we can see. Anyway, if I go ahead, I'm gonna do it one more time in front of you. Do you remember? Somebody remind me. So now it's just like, now we are thinking. So what is the procedure I have done many times in front of you of designing a project? First of all, which file I have to create, if you guys remember?
Usually start with the design source.
I start with the design source, or I started with creating
Constraint.
Well, you can start with the constraint too.
XDC file.
XDC file.
Yeah, you could do that too.
So no, yeah, fine. Nexus. Then we'll go here. Yeah, because I don't remember, Nexus is for XDC files. So I'm gonna go here in GitHub or Digilent website, whatever, Copy. Fast. Here. Then I will go and say constraint have been created. Go there and just go there. Right? The second step, I should do what?
Add design files.
Exactly. It's not add, create. Because we don't have it now. Or I have it, but I would prefer to do it multiple times in front of you. So gonna be here what? Counter. Right? Then I will just say finish. I know my counter is gonna be what? Is it gonna be control counter or just a counter? Pretty much, if you would like to have a generator, it should be not control counter, unless you would like to stop the power. Okay, here's a story. One of the philosophy that, you know, when we get tired, we go sleep or not. When you go sleep, what exactly you do? Majority of your body will shut down, except the minimum thing will be still on, right? Like your heart rate, the heart is like beating up, you know, your conscious is like, you know, doing some other stuff for healing the cells in your body and so on, right? Same thing that, you know, when you will go in your computer and you say that, you know, stand by or, you know, sleep. So basically you're not sucking too much power. If you would like to make low power design, it's better for you actually to control the clock. Sometimes this piece of the module, you don't want it to have the clock all the time. Then you will turn it off. Then you're gonna make a controlled count. Make sense? So now I'm gonna say I need a clock. And then I need also reset. And then I need what? That's not controlled. I'll just say output. And I'm gonna make it a box. Then I go in my counter here, and I will start sorting my code. One of the things I actually would like to completely mention, yes, writing structure is very important for storing data, but sequential, at least building flip-flop, I would recommend to do with what? Behavior. Like, you know, this is behavior. Then, you know, I want it to be parameterized. I like parameter stuff. So basically gonna be parameters. So I'm gonna make it like this and say parameter, and I say what size equal 16, right? Then I go there and I say that, you know, here's size -1, right? And from there I say always procedure block, right? At pos edge of the clock or neg edge of the, yeah, make it pos edge of the resets. Then begin. Then I say that, you know, counting generate. Then from there I say F reset. Then, you know, it's just a one line. So you can say that, you know, OB equals 0. Then else OB is equal OB plus 1. Right, we build the count. Everybody agree? I intentionally made it like one line without begin and end to show you that, you know, if you are targeting single line to control, you don't need begin and end. But if there is another one, let me say that something, right? Let's say any things, like, you know, let's say, you know, wire, not wire, make it rig Tim, just something, right? Look what if I do now. I will do now, I say Tim, right? Equal 0. Look what will happen. Error happens. Have you noticed? Else consider it an error. So in that case, you have to go ahead and say here, begin, end, then else will not be error anymore. Is it clear, everybody, for what I have done now? Clear? Hello?
Mm-hmm. Essentially, they're brackets.
Exactly like brackets. Okay, now the third one, which is the one we would like to see, is the simulation, right? So gonna be counter TV. So we say here finish, and from there we don't need input output as we said in the dispatch. So in that case, excuse me, in that case we just go ahead and take this, guys. I remember word by word, so I gotta go here and say counter, and from there I can just go like this. And if I like to be very organized person, I can just go ahead and make here parameter, and I call it size TB equal 32, for instance. And from there, I can call the counter, and I call it size TB equal, no, size equal size, and then what was the name of it? Let's say count, or maybe, you know, gen count. Begin end are used to define the scope when there are multiple lines in the F7. Exactly. And then, you know, we're gonna go here and say now it was clock and reset and OB, and of course we have to do what? The input will be reg, and the output is gonna be wire. So it's gonna be ISTB right. Okay, now we're gonna go ahead and just put here clock, we'll put here reset, we'll put here count, and we need generating the clock, right? So gonna be what? Initial begin, and say here clock equal 1, and then gonna be what? Initial. Then we go here and say always. There is another way to do it, but I'm gonna leave it for later. So it's gonna be here 5 clock equal. You know what I'm doing, right? This two procedure always with initial block is basically, you know, the clock, it has to be in the beginning 1, and then, you know, after that, you know, you keep flipping every 5 nanoseconds, which is the 10 nanosecond, right? The 100 megahertz, the 100 megahertz. Now, you know, I'm gonna make it initial. Everybody's following me, right? And here what? Running. We don't need it even, because, you know, it's just like running now, right? We're not controlling anything else, so basically that can be enough. No, we need it. We can come and say begin, and say, you know, initial begin, maybe reset is equal, in the T is equal 0, reset is equal maybe 0, then, you know, in 10 nanoseconds, reset is equal 1, then, you know, in 20 nanoseconds, reset is equal 0 again, and then, you know, I leave it running for maybe 1000 nanoseconds. That doesn't need an parameter. No, you don't need the parameters for the test bench, because it's an always, it's basically gonna be like a while loop, open while loop. You cannot get out of it. But then, you know, somebody will come and say, oh, but you have an open loop, but why the other pieces are still working? Because, you know, it's a parallel language. So it's made that thread running in parallel for clock while the other doing some other initial blocks. That makes sense? Anyway, so gonna be here, maybe we can put some duration 10 nanoseconds. There is a way to do it. I will show it to you later, 10, maybe 100 nanoseconds, and then, you know, we can come and say finish. Then end. Let's see the test bench, and then, you know, behaviorally we can see. Here's the values. Look, if I open here, look what happened. Can you see this? Everybody can see it? Now I have the counter in the beginning. In the beginning, it came here to be don't care. Somebody tell me why. Do you have an explanation why this came like that?
It wasn't given a value yet.
It wasn't given a value yet. So we said in T0, I don't know. So basically I said the reset is equal 0, but the reset is responsible of setting a value to the counter. So at that time, you know, it was like, you know, what exactly I should do? I don't know. So that's why, you know, in a cycle, which is 0 to 10 nanoseconds, it did nothing. Then, you know, in 20 nanoseconds, I designated, if you look here, it's going to be 20 nanoseconds is written there. See my cursor? You know, the counter filled with 0. Then after that, start like going to 0, 1, 2, 3, whatever, like, you know, value-wise. We can just go ahead and make it radix and make it unsigned. So it can be 0, 1, 2, 3, 4, 5, 6. But the counter itself is a bunch of bits, right? So if you go in a way button here, you will find that, you know, it started to act as a clock. So this is a clock, right? If you stand on the shift with the left click, it will generate a new cursor. So give you now 20 nanoseconds. Remember, what was the clock? What was the clock? The clock, it was what? So 2 of the clock became 1, right? Look. Did you see that? Which is proving that, you know, 0 bit on the counter is basically in the maximum frequency divided by what? By 2. That makes sense? Everybody follow me, or it's a little bit, hello?
Can you explain a little piece again?
Should I do it again? I should explain it again?
Yes, please.
Sure, Eduardo. So let me go back to my tablet. So F is equal to 1 over T. Everybody agree? So the maximum frequency of the first one is basically here. F of the bit 0 is equal to the maximum frequency divided by 2. That makes sense? Then if I would like to have the T of the B0, it's gonna be what? It's gonna be 1 over F divided by 2. That makes sense? So that mean is 1 over T times 2. No, sorry. It's gonna be T times 2. Right? Because, you know, 1 over F is the T. And over 2, that means it's equal to, right? So in that case, if the duration of this one is 10 nanosecond, the duration of this one is gonna be what? Huh? 20 nanosecond. Make sense?
Yeah.
Then if I take the 20 nanosecond and flipped it like this, what is the maximum frequency will be? Huh? It's gonna be 50 megahertz. Here, that was 100 megahertz, right? Divided by 2 is 50 megahertz. So this is equal to this, right? That makes sense?
Yeah, it makes a lot of sense. Thank you.
You're welcome. Now the second bit, what it will be? So the second bit, it will be F of the B1 is equal F as a master clock divided by the 4. So in that case, it's gonna be here F is 100 megahertz divided by 4. So what is the value will be? It will be 25. 25 megahertz. If you flipped it 1 over it, what will be the output?
Is it 40?
Yes.
Nanoseconds?
Yes. That makes sense?
Yeah.
So that's a systematic way of doing this. We can take this into the old example we made and see whether they're gonna flicker. Your eye will recognize the flickering or not. That makes sense? So we are putting pieces now. So if I go now into the, if I go now back to Vivado, okay, so I can go get like this, and I can go exactly as I see, you know, here. I found it is actually what, this is just like one, so I'm sorry, so we have to do it like that. The second bit, see, it's 40 as you said. The third bit, it will be what? It will be this one. So gonna be, you move forward, right? So, you know, divided by 8, and then, you know, that will be divided by 16, so gonna be this one. And then, you know, divided by whatever other one, you know, divided by 32, gonna be this one, and so on. That makes sense? Now we don't need this anymore. I just need to turn it back to the old example we made, right? So it'll take some time. So here we say close project, and we need to turn it back to our old projects. What was our old project? It was counter, right? So do you remember this one? That was the example when I ran it in front of you on the board. It wasn't flickering enough. That makes sense? Now, we can add into this. Everybody agrees me? Either I can make a module, it's called clock, counter clock divider, and I call it there as an instantiation, or I just make another always block. So I can make another always block here. It's called, it's easy. So I can just say reg clock div, right? And from there, let me put this on the side. So I can say clock div, right? And I'm gonna teach you something new. So basically, I can come and say rig, and then I can make also something that's called rig counter temp, and that will be 32 to 0. I'll make it 16s maybe, right? Then we can add here into this another switch. It's called input, and that switch will be 3 to 0. And from there, I can say max control. And I will tell you what is the reason. What I'm gonna do, I'm gonna play with the speed. You know what I mean? I'm gonna select multiple speed. So from there, I can just go ahead and say that, you know, always at pause edge of the clock, or pause edge of the reset. And from there, I say begin end. And I can say here F reset. And then I can go ahead and say count temp equal 0, else count temp is equal count underscore temp plus 1. So what I did here, I built the generator, right? Gen count. So far so good. Why I need the clock div? The clock div will be the new clock here. So gonna be clock div. Everybody understand what I'm doing? Hello?
Yeah.
Okay. Now I'm gonna make a mechanism, which is a combinational circuit. I can make a multiplexer using something that's called key statement. I didn't give you key statement. So basically it's gonna be here always. And from there I say max count. Again, and they're gonna be what? Selecting feed. And then I can say case max CONT.
And these case statements are most definitely behavioral, correct?
They're gonna be behavioral, perfectly behavioral, you know? Always at. So have you noticed the always block now, we use it for what? Even combinational, because it's a combinational circuit, right? But the sensitivity listed has a what? It's not a clockwise, right? So now I can just go and say, you know, in 0, what will happen? In 2, what will happen? I can say 0 like this. Log div equal count temp, and then, you know, 0. And then you saw here default. There's something called default div, and you can make it what? 1b z. So you know what does default mean? In case statements, they are believing that something wrong might happen in your circuit. So in that case, the default will be used as an emergency. You will never see it unless you broke something. You know what I mean? What I'm saying there, I'm saying in default, make it open circuit so nothing wrong will be shorted. You understand what I'm saying? This is for emergency here. Default for emergency.
Professor?
Yes.
In the book, it didn't specify, but the default case, does it go after the rest of the cases?
No, the default is basically like the case that, you know, is when, you know, imagine that, you know, I have this say, imagine that, you know, I have maximum count is how many bits? It's 4 bit, right? So that means how many choice I have under this case? 16, right?
Correct.
So if I have 16, then, you know, if none of them happens, which is basically something wrong happens, then, you know, default will happen. You understand what I'm saying?
But programmatically, do I include it after the rest of my cases?
Yeah, I understand, yes. But you can put it up, I believe. I don't think there would be a problem if you put it up or down. But in general, what I'm saying, this is used for the emergency.
Mm-hmm.
Because, you know, imagine that you already put all the possible 16 cases, right? What exists still? What is left? Nothing, right? But because error might happen, especially if you are launching rocket and it's in a space, and then, you know, there is radioactive activity up there, right? Then, you know, default might happen. Then, you know, in that case, make it open.
Okay,
Another thing that I want to mention, it's very important. If you use case statement, you have to fill all of the possible cases, even if you are not using all of them. Example, now I have count temp is covering 16s, right? Cases. But then, you know, I just need the first 12. There is 13 and 14 and 15, I didn't use them, right? If I don't use them, the compiler will consider them latches. So you have to tie them to something, tie them to 0, to the ground, whatever, you know? Is it clear? Hello?
Yeah, that makes sense.
So we just had to instantiate a value to them.
To something. So yeah, just like, because don't forget this is a behavior. And you have to be sure that the behavior will not misunderstood, right?
Yeah. If you were to leave them out of the case statement though, would the case statement not just refer to the default if it were to get?
They will go to the default, exactly. They go to the default, but the compiler will consider them latch. 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm gonna be here. I'm doing it not in a very smart way for a reason, because there is another smart way you can do it, okay? Which is also using some for loop, but not the for loop we are using. So that's gonna be A, B, yeah, okay. Now I'm using what? I'm using the decimal radix, right? Everybody understand what I'm doing, right? Those are decimal radix. If I would like to make it hex, there is a way to do it hex, like, you know, here. Look, I can just come and say there are 60, there are 4, right? So 4 H A. Same thing of representing the pointing. Do you remember when I was doing this before? So now it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So everybody understand what does it mean, right? Now I generated a wide bit range of bits representing multiple clock, but with the equation of the 2 power something divided. And then, I made a multiplexers to select which speed. And then that speed will go into the counter that, we're going to use the stop and pause counter. That makes sense? If I go ahead and, I modify this to be connected to the XTC, then, max count has to be defined somewhere, right? So I have to open my XTC. It was from the last time. And we have maybe the last 4 switches can be designed for this 1, 2, 3, 4. So those guys will be like this. 1, 2, 3, 4, and that's gonna be 0. That's gonna be 1. That's gonna be 2. That's gonna be 3. Is there anything else we are missing before the generating the bit stream? So we have this one, we have the count, we have the max counters, and so on. And we know this counter is gonna be designated as a parameter 4, so that's gonna be counting 4 LEDs. And we know those LEDs are gonna be in a count. So if we go back here, so the pin LED is gonna be count 0, 1, 2, 3. The pin from the right side of the board, it will be that, right? Now I can safely say that, generate bit stream. When I say generate bit stream, by the way, what will happen, it will run the synthesis first and finish synthesis to implementation. From there, you're gonna go and generate bit stream. Or you can do it in just run one by one manually as you're doing. Is it clear?
Yes.
Let's see, take some time for about that. If you want to make the multiplexer of the case statement, how you can do it from the 2x? You can make also generate, you can make it with the 2x1 structure, and then you will make 4 gen, right? And you will make it loop. That makes sense? You understand what I'm saying? Hello? Do you guys understand what I'm saying about, instead of the case statement, you can make the structure. You build 2x1, and after that, you will use 4 gen to have the multiple propagate the levels. So already you have 4 bit, that means 4 levels of the, let's say 4 levels of the multiplexer will be concatenated to each other to build 16-1 multiplexer. That was from the 2300 knowledge, if you remember. So look now, we have 7 lookup tables and 20 what? Flip-flop. Do you like to know how many flip-flop we have? I can tell you. Look, the counter we built here, right? It's what is the size of the count temp? Huh? 16 or 17 even, right?
Yes.
We didn't take the rest of it, so it will be eliminated. This is something I want you to understand. What happened, it counts 0 to 15, right? But I didn't think 16. 16 when what?
Became a latch.
It's not latch. The compiler remove it. So the counter basically mapped by the 4 bits, so that means 16 flip-flops. Then, the historical counter we built, it was 4 bits, so 4 plus 16 is 20, right? That's why I give you 20 here flip-flop. So now I use the minimum number of flip-flop for optimizing my circuit. Is it clear? Then, what is this 7 lookup tables are? It's, what is this for? This is, majority of it for the multiplexer we built here, and one of it just for the STBS. When we said, when STBS is equal 1, go into the counters, otherwise don't do anything. So that was lookup table. So that's 6 lookup table on the top plus 1, 7 lookup table. So see, I counted number of resources even before, the synthesizers give us the result. That's a skill you need to learn. Sounds good? Have you noticed something? Any of the hold time and setup times are negative? No, it's a positive or 0. Positive or 0. That means my design is what? Perfect. Look at my maximum frequency, total power. Do you see it? 0.109. So that's why I work in the low power. Now I'm going to show you something. Then I go and open the timing report to show you the slacks. So cover everything of whatever we discussed today, right? So here is my board. Everybody see my board very well, carefully. We have the Digilent demo on it, right? Then I will go ahead and say open hardware manager. And from there, I say, go ahead. Automatically, it will call for the chip. If it's not identifying the chip, that means your USB cable need to be changed. It identified it there. And then I say program device. The bit file stream, it's already generated without any problem. And I say, go ahead and do it. Now, did you see what happened? Basically, the counter is counting, but it stopped. It's completely problematic. So we need to play with timing here. Still, it's not speedy enough. So I think we need to go more into the lower frequency. So what we can do, we can actually make it here selective. So that means maybe we can make it 5 bits. Okay. So in that case, we don't need to make it 5 bit. Actually, we can make it actually still 3 bit. But the counter here, it will be 31. So 32, and then we can go ahead and say that pick up the like the 16th, 17th, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 29, 30, 31, and we don't have 32, so basically you can just make it what? 0. Okay, so now I forced the thing to have all the counter possibilities. If I go ahead and say run generate bit stream, then still number of the flip-flops will be increased. So let's see whether that's happening or not. So you can just go like that.
Professor?
Yes, sir.
Did you mean to skip case for you didn't initialize count temp 28?
Which one?
In the always for mux, there's no 20.
Which is fine.
Okay.
I'm just dumping stuff. I agree with you. You're right. That's why if I make it, then it will be fit to 31. You're right. I'm just trying to lower the maximum frequency as much as I can and max multiple clock to feed the other counter. You know what I mean? So our eyes visual system, I believe, work in kilohertz or something. So then, if I go in a kilohertz or lower than that, your eyes will recognize that, the flashing. Later on, next week, I will be telling you that the time maxing on the 7-segment display, and there you will be able to see number going up and down, and then we will have a good lab about that. That makes sense? Is it clear, Louis?
Yeah.
Let's see. Look what happened. Number of flip-flop increased to be what? 36. Which is the 32 plus that 4, right? But then somebody will tell me, oh, but you didn't call all different counter inputs, but I forced the compiler not to optimize because I put here 0 and I put here some other number like 28 I missed. So basically the compiler now understood that he doesn't have the luxury for making for me optimization. The older version of the tool ECE wasn't that really smart, so it was sometimes optimize what you want and give you whatever you don't want. That makes sense? Clear? So going in the routing. And the implementation figure out basically the same number of resources are used. Let's see what would happen. I have a news for you. Maybe I can cause some timing issues for you if I do some other tricks. And the other trick I can do, I can increase the multiplexer size to be huge number of elements. In that case, it's going to be huge combinational circuit. Critical path will be stretched. Then timing issues will happen. That makes sense? Still, I'm into the power of 0.019 because the stages of the sequential are still the same. And the timing, still we meet the timing. Now open the hardware. I have to go ahead and turn off my board, turn it again to be sure that the flash is actually what? All flash. So I go in here and say open target. And from there, I can just say, go ahead, please. Open device, program, and for programming is still in front of you what is fixed, but when look what happens. Everybody can see now? Hello?
Yeah.
So what is happening now? Flickering happened in a certain specific location. The location it was 011 is number 6. So in number 6 here, 22, so that means 2 power 23, right? So maximum frequency divided by this number, your eye, human visual system recognizes. Make sense? Any questions so far? Let me show you also the report of the power, because I noticed one of you in the Slack was saying that I didn't understand what he meant by the total power. So I want to be sure that you guys understand what I'm saying. Total power, it's distributed between pieces of the hardware. So if I go ahead and say that reading the net list, I'm waiting for the net list. Take some time. When I say power, you have to set up some timing, like power supply. This is timing coming from Digiland. Switching, you know what switching mean? That means that the power consumed while the clock is going on and off, positive edge, negative edge. And the outputs, I don't care about it. Experiment, basically we are in the Earth, so we are in respect of the 25 Celsius. And just go like that. And now I'm gonna do something. Look what happened here. Everybody can look to me very well. The definition of the power came into multiple pieces. So total on the chip power is 0.11, which is fine. What? Dynamically, it's represented into pieces. Look, dynamic and static. What does static mean? It's just IO and combinational. Dynamic, that means is involving clock. So what is involving clock? Clock itself. And it's telling you what is the pieces of the clock. Like, look, now the buffer, or which clock? Is this the real clock or the one, for the buffering, or so on? Then hierarchy again, you go into the 12 and the def and all this information, power supply, margin. And then, signals, how many signals we are using? We are not using that much signal. We're using the clock div and the STOPS. And then logic, we don't have that much power for the logic. IO, I'm just using LED and switch it and not sucking too much power. And those actually under the dynamic. Static, it's something fixed you cannot do that much with, and it's taking the majority of the 0.11 power, which is the 89%. That was for the synthesis, but for the implementation, which is the more accurate, the power will be different. So we can open it. Here's the numbers, which is kind of similar. The timing report is here. Everybody can see my timing report. You can generate it from here. Edit timing constraints you can play with. Report timing summary. That's basically what we need. We can call it timing 1, and from there. Have you noticed what is written in front of you? All user specified timing constraints are met. What does it mean? It means that we didn't have anything negative. Who is actually the one who's responsible of this? The initiation coming from the XDC when we use the clock 100 megahertz. Is it clear?
Yes.
Okay. So any questions so far for whatever material we already discussed today? Anything is confusing you guys?
Yes, I had a quick question.
Sure.
Just like how we have a clock divider, do we have a clock multiplier as well?
Yeah, PLL.
Okay.
There is no way as a digital to amplify clock. You have to use analog. In that case, the analog on the chip is PLL. And I already run the PLL in front of you, right?
Mm-hmm.
We can find an application. Maybe if we have time, I can make you a crypto processor, like in week 12 or 13.
Mm-hmm. Couldn't I multiply by a factor of 2 by instead of making it activated on the positive edge, the rising edge, I can make it dual edged?
Yeah, but as I told you, nobody do this. I made a US patent for it. It was really it's the considered future technology.
Wow. Okay, thank you.
You're welcome. The one who funded me, it was DARPA, Department of Defense. Any other questions? Before I leave, is there anything complicated so far? Is there anything that's not clear? Please don't hesitate. I'm here for helping you. Okay, you guys, I think I will need to rewatch the lecture to be sure. Sure, definitely, don't hesitate, just contact me. Another thing, if for those people who think that, the opportunity of the funding, it's good for them and it fit them, please apply. It's not bad for you to have good money with you, I was a student and I know how it works. Okay, look.
That funding only applies to first-year transfers and sophomores, correct? I believe that was a hard value.
It's not a problem. I will find, if I find any other opportunities, I will pass it to you guys. I think there is something it's called NSF program. Also, you can try. Okay. And there is something also called SMART. Have you guys heard about it? It's from the DoD, Department of Defense. It's called SMART. You can guys search for it. It's called SMART. It's SMART. There is another one. It's called Cal Reg For you, for those people who would like to continue with PhD, they can go in a Calbridge. Okay, doke. Okay, God bless you. Stay safe, and I'm really enjoying the class, and I'm enjoying talking to you guys, and I hope you guys also are enjoying the course. Thanks so much. Have a wonderful day and stay safe. Thank you.
Thank you, Professor.
Thank you, guys.
I have a question, Professor.
Sure, sure.
Is it possible to make a flip-flop with structure modeling? Because I found that if you do it with like NAND gates, the Vivado doesn't see it as a flip-flop; it sees it as like a combinational logic instead of sequential.
But it decreases your it decreases your power.
Yeah.
Right?
Yeah.
Yeah, see? So the trick works. Right?
Well, I was asking that because I tried making the flip-flop both with behavior modeling and structural modeling. When I use structural modeling, the Vivado doesn't see it as sequential logic, but rather as combinational. So it uses lookup tables instead of using flip-flops, which we
Yeah, I
want.
understand you. Yeah, I understand. Yeah, I understand. But you did a good job. That's basically what I want to say. The trick you did, it helped you with the power, right?
Yeah.
Next time I will share with you some equations for power that might help you to design better. But I just want you to dig by your hands so you will learn more.
Okay, thank you.
Okay, thank you. God bless you. Okay, guys, thank you. Bye-bye.
Actually, Professor,
Yes, sir.
where can we find the office hours sign-up page again on Blackboard?
It's in Calendly. Some people already have it. They already signed in Calendly. I see now.
I see. Is the link to Calendly on the syllabus, or?
Yeah, you will find it. You will find it on my syllabus. Just click on it and find the time slot.
I see it.
Okay.
Alrighty.
Thank you. Have a good one. Stay safe. Thank you.
You too.
Bye-bye.
Thank you.
Bye, everybody.